Let's dive right into this explainer and tackle one of the absolute biggest headaches in artificial intelligence right now, the cold start problem. Today, we're unpacking some seriously fascinating insights from Paper 4 of the USDF trilogy. You see, traditional AI systems, they're kind of stubborn. They tend to just force a single learning objective onto all incoming data, totally ignoring what that data actually is in physical reality. But what if, and this is the big question, what if an AI could act a bit more like a biological brain? What if it could instinctively route data based on its physical properties before it even tries to figure out what the data means?
There's a quote from the research that just brilliantly hits the nail on the head regarding the biological drive behind this whole architecture. It describes an end-to-end pipeline that mirrors the human brain from the moment light hits the retina to the moment a long-term plan is formulated. That's exactly what we're exploring today. We're looking at a system built to perceive its environment reflexively, literally just like our own sensory cortex. Before it sits down to make complex, deliberative plans, it acts on pure instinct. It characterizes the raw physics of a signal in literal milliseconds.
So, let's boot up the directory and see where we're headed. We'll be walking through 1. The sensory reflex arc. 2. The 1D signal baseline. 3. Expanding to 2D images. 4. Entering the 3D volume. 5. Real-world medical validations. And finally, number 6, the universal methodology. All right, kicking things off with Section 1, the sensory reflex arc, where we talk about bypassing brute force deep networks. This is the bedrock of how the system first encounters raw data without immediately agonizing over what it's looking at. The idea of a prism perfectly captures the essence of the Universal Signal Decomposition Framework, or USDF for short. It completely skips the immediate, heavy-lifting, brute-force deep network processing. Instead, it disentangles these raw, chaotic signals into neatly partitioned, structured frequency bands. Think of it like a reflex, separating the frantic, fast-moving, chaotic data from the slower, highly structured data. And from there, the data pulls right into the frequency-governed self-graph reasoning, or FGSGR framework. This setup perfectly mimics mammalian cortical oscillations. The data essentially flows upward. It starts down in the fast reactive gamma tiers, handling immediate things like sudden feature binding, and moves all the way up into the slower, deliberative theta tiers, which are the parts handling long-term planning and episodic memory. Now, the real star of the show here is the diagnostic router. It acts as the ultimate gatekeeper. Before any heavy computational lifting even starts, this router uses fast Fourier transforms to calculate these super cheap mathematical fingerprints of the data in milliseconds. It literally reads the raw physics of the signal, and then dynamically picks the absolute perfect unsupervised learning recipe. Boom. The objective selection problem? Solved instantly. Moving right along to Section 2, the 1D signal baseline, establishing the sensory uplink. Let's look at how this router handles basic, raw one-dimensional data, things like audio tracks or biosignals. The router's logic tree for 1D signals is, honestly, elegantly simple. Depending on whether a signal's fingerprint reveals it to be transient, broadband, or spectrally concentrated, it routes that data to a highly specific, optimized recipe. So, if it detects sharp isolated anomalies, it sends the data straight to the USDF_wide recipe. If it's just a smooth broadband signal, it routes it right over to USDF_default. And the results are kind of incredible. Across a really diverse 7-dataset 1D benchmark, testing everything from audio chirps to complex harmonic stacks, this routing methodology hit a 95% labeled tuning recovery rate. It flawlessly matched 4 out of the 7 datasets to their absolute ideal, perfect fit recipe right out of the gate. Okay, Section 3. Expanding to 2D images, translating fingerprints to spatial grids. A biological reflex is great, but does it actually work on pictures? Let's bump up the dimensions and test the spatial limits. What's genuinely fascinating here is watching how these mathematical fingerprints gracefully make the jump into a higher dimension. A 2D image obviously doesn't have time, the way an audio signal does, right? But it does have spatial frequencies. So, for example, the 1D concept of envelope kurtosis, which is used to detect sudden audio clicks over time, mathematically translates directly into gradient kurtosis for a 2D image, which detects sharp visual edges. The underlying math of the sensory reflex stays exactly the same. When they scaled this up to 32 by 32 pixel images across a totally new 7-dataset zoo, the methodology held up beautifully. The diagnostic router achieved a 93.2% recovery rate.
And it actually got better at its strict recipe matches, nailing the perfect objective recipe for 6 out of 7 datasets completely automatically.
All right, Section 4, entering the 3D volume, voxel-level diagnostics. We've mastered flat 2D images, so let's push this boundary even further into the 3D volume and deal with those complex 16 by 16 by 16 voxel grids. Now, voxel grids are notoriously difficult to work with. Think about it. 3D data fundamentally lacks the continuous temporal flow of a 1D signal, and it totally lacks the flat, predictable regularity of a 2D image. But the researchers? They didn't change the playbook at all. That exact same core sensory diagnostic logic, looking at spectrum peaks and gradient kurtosis, was deployed identically in 3D space.
And the outcome was just staggering, a 94.3% recovery rate. In fact, the 3D router achieved the highest strict match rate yet. It scored a perfect 7 out of 7 on the synthetic 3D zoo. It instantly matched every single dataset to its optimal learning objective just by glancing at its unlabeled mathematical fingerprint. No way, right? But it works.
Which brings us to Section 5, Real-World Medical Validations, the ultimate diagnostic test. To actually validate this, and to see if it could genuinely impact healthcare and real hospitals, the researchers had to unleash this pipeline on real-world data. They stepped out of the synthetic lab and ran it on 9 different real-world medical imaging datasets. Looking at actual clinical modalities, everything from 2D ultrasounds to complex 3D CT scans, the system showed some incredibly powerful transfer modes. Just look at the pneumonia dataset. It saw a massive 41.9-point performance lift on pediatric x-rays, with the router hitting a strict match. Whether it was breast ultrasounds or blood vessel MRA scans, this reflex arc effectively evaluated the raw medical data and successfully routed it to the correct AI recipe.
Now, of course, it's not literal magic. When they tested it on a dataset dealing with adrenal gland CT volumes, the system did hit its confidence boundary. Because that dataset was severely imbalanced, we're talking 78% normal cases to just 22% adenoma, the system basically collapsed to the majority prior. But honestly, this perfectly proved why balanced resampling is just an absolute necessity in medical AI if you want to reveal its true discriminative capacity. But here is the truly brilliant part. When the system fails, it actually knows it's failing. It has this built-in diagnostic self-monitoring property. So when it runs into data with features that don't match any clear recipe, like, say, the soft, squishy cellular membranes and electron microscopy neuropill, it issues a totally honest, ambiguous region warning. This immediately alerts medical practitioners that the AI is operating outside its safe, characterized regime, which completely prevents blind reliance on failing algorithms. It's a real game changer.
Finally, Section 6, the Universal Methodology, Dimension-Independent Reasoning. Let's pull all these amazing threads together and reveal the central finding of Paper 4 in this massive USDF AI research trilogy. The ultimate takeaway here is this really powerful paradox. The specific AI recipes, the distinct training objectives and augmentations that work best, are strictly modality-specific. A masked autoencoder that works wonders in 1D might feel completely in 2D. But the overarching diagnostic methodology, the actual procedure of extracting physical fingerprints and using a rule-based router to pick an objective, is entirely dimension-independent. It works beautifully and uniformly across 1D, 2D, and 3D realities. This hands the AI community a completely replicable 4-step biological blueprint. 1. You build a diverse dataset zoo. 2. Characterize your objective recipes. 3. Identify cheap, raw mathematical fingerprints. And 4. Calibrate simple routing rules. This procedure lets you dynamically route and process data at a reflexive level, completely regardless of what the data actually looks like.
And that leaves us with a genuinely fascinating provocation. We've just watched this biological architecture seamlessly jump dimensions from flat audio lines all the way up to complex, volumetric medical scans. So what kind of unimaginable capabilities are going to emerge when we unleash this exact same sensory reflex arc on even higher dimensions? Think immense graph networks, complex point clouds, or time-frequency tensors. The blueprint is already there. The dimensional jump has already begun.